Hello everyone, welcome back. After a long hiatus, we are continuing with organic chemistry, which we are going to practically fly through after this. We are doing 3 chapters today, all of which are associated with one another and lead into one another, which is why we sort of put them together. Thank you guys so much for the support on the YouTube channel recently. We hit 25,000 subs while I was away on vacation. So I have to do my 20K subscriber special that I didn't get to record because I got busy will turn into a 25K subscriber special. I'm releasing a Q&A document. Any questions that you guys have about me, my life, the MCAT, this, that, the other thing can all go there, and I'll be more than happy to answer them. I'll leave in the link in the description, and I'll pick out the best questions and I'll answer them. It'll be like a little way for you guys to get to know me and the history of this channel if you care. And if you don't, go away. So let's begin. Thank you for your support. And now, in return, I will torture you. Alcohols. Alcohols are a specific type of functional group inside of organic chemistry. And alcohols are created by the attachment of hydroxide groups onto carbon backbones. Right? These hydroxide groups are OH. So this tells us a couple things about alcohols. Number one is that they are polar, not only in their connection from the carbon to the oxygen, but also in their connection from the oxygen to the hydrogen. Correct? Number two, another thing to mention is that alcohols do not have double bonds or triple bonds as part of the functional group. So for example, is that a alcohol? No, that is a protonated carbonyl, right? No double bonds allowed within the functional group. But if I were to take this and erase this double bond right here, is that an alcohol? Yes, it is. So it's a single bond between the carbon and the oxygen, and obviously the only thing allowed between the oxygen and the hydrogen is a single bond. So things like this are alcohols. This is an alcohol. Something like this, is that an alcohol? Yes, because the double bond isn't within the functional group itself. I said hydroxide groups on carbon backbones. That's a carbon backbone with a hydroxide group. It doesn't matter that the double bond is on the carbon that's involved. It just so happens that this alcohol exists on a carbon that is sp2. Correct? We'll get more into that in a little bit. Does that make sense? And you can also have things known as diols, 2 alcohols. That look like this, and that look like this. We went over this in our functional group like nomenclature lecture, right? Where this is a vicinal diol, they sort of live in the same vicinity, and this is a geminal diol, right? Vicinal, geminal. Vicinal on the left, geminal on the right. Fragrance of the day, since a lot of people care on YouTube. I am wearing Reef 11, a really nice pepper, jasmine, sandalwood cologne. It's a little feminine, but I kind of like it because my house always smelled like jasmine growing up. Jasmine is my mom's favorite flower. Okay. What else do we have to know about alcohols, guys? Huh? Yes. Another thing we need to know is because of the access to this OH group, not only are they hydrophilic, which we knew because of the fact that they were polar, but I think what you're getting at is the fact that they form hydrogen bonds, right? These have H bonding, which means that as opposed to something like this would have a much what? Higher or lower boiling point? Higher, because of the increase in what? Increase in intermolecular forces, and that intermolecular force specifically being the hydrogen bond, right? And this is a big part of the reason why, if you have something like ethane, right, or let's say you have butane or whatever it may be, a hydrocarbon, you leave it out in the open, it'll evaporate immediately. But for those of you who have experience drinking alcohol, you realize that like you can pour it and it'll stay liquid for a bit, but it will slowly evaporate away, right? Whereas water, it'll evaporate away very slowly, right? That's the increasing number of hydrogen bonds that's showing you the increase in the boiling point of those specific compounds. So 3 is hydrogen bonding. Next thing we need to know is this. Hydrogen abstraction and addition. Because of their similarity to water molecules, only the second hydrogen in the water molecule being replaced by an R group to make an alcohol, these are what we call amphiprotic. That is to say that they are capable of being protonated and deprotonated. That the protonation of an alcohol, we'll take it from ROH, that's an alcohol backbone, right? That if we were to protonate this alcohol, we would make it ROH2+, a positive charge. And if we were to subtract an H+, we would make this RO-, reflective of the fact that from water we can get OH- and H3O+. Notice that one of the hydrogens is replaced with the R group, right? This is the backbone of alcohol chemistry. Does anyone remember what reaction alcohols are actually an important solvent for when you're trying to do them? Their polar protic capacity makes them a good solvent for what type of reaction? Huh? SN1 reactions and? Neutralization reactions. So you can protonate, deprotonate things with alcohols, number one. You can swap off those protons. But I really was looking for the SN1 answer, right? That SN1. So let's take a look back. This was part of our, I believe, analyzing organic reactions video, if you guys have watched that recently. The SN1 reaction begins with something known as a polar protic solvent. Because of the fact that we know in the SN1 reaction profile, we make a lot of polar and charged compounds that need to be solubilized by something that is polar. We need the solvent to be able to dissolve everything inside of that flask, so it must be polar. Why does it need to be protic? Let's take a look at the SN1 reaction profile one more time. We're going to have a leaving group, a very, very weak base that's going to leave and be stable by itself. It's going to leave spontaneously off of a carbon backbone that leaves behind a stable carbocation. That stable carbocation is going to get attacked by what? Any alcohol that you put inside this flask as a solvent, the solvent plays a part in the reaction. So acting as a Lewis base, donating electrons into an electron deficient region of the molecule, we are going to get the attachment of the alcohol. And remember that we have now created chirality here. Star indicates chirality, plus minus indicates a racemic mixture. Why have we created chirality? Because at the point of the carbocation, we have a p orbital that can be attacked on the front or the back face. You guys remember that, right? So attack on either side of that will give you an R or an S configuration. Anyone following me? Yeah? Why do we need, now, this was the question. Why do we need a polar protic solvent? Why do we need the solvent to be, anything wrong? Why do we need the solvent to be protic? We need the solvent to be protic because, look, when the solvent attaches here, we need to deprotonate. And with the deprotonation, we need to use something other than the leaving group. Why? We can't use the leaving group because the leaving group normally comes from a strong acid. So we can't reform a strong acid in this flask. It's not possible, number one. Number two, the solvent is in such excess that it's going to react with whatever you have in the flask rather than the leaving group itself, right? Okay. So now we have to deprotonate this. So number one, the solvent that we attach needs to be able to be deprotonated, but also the thing that deprotonates the adduct, this is called an adduct, when you put something on a molecule and it looks like something else. So this is an alcohol adduct, right? When you deprotonate the alcohol that's on the carbocation or attached to the carbocation now, what are you going to use? You're also going to use the alcohol itself. So the alcohol needs to be able to be protonated and deprotonated. Does that make sense? You guys get that? So I'm going to show you one more time when we're done here. ROH is going to take this, and this is a Bronsted-Lowry reaction, right? Acid-base reaction. We get plus minus OR. And that's your SN1 reaction, right? So you see here, the alcohol attached and needed to be deprotonated later, but here the alcohol needed to be able to be protonated. That is the amphiprotic nature of an alcohol. Alcohols and water have this capacity. What would happen if we did this with something that wasn't amphiprotic, that wasn't protic? Let me show you. You would have a carbocation, and let's say you use something like diethyl ether. You would attach here. Now what? What are you going to do? Rip off the ethyl group? You can't. You can't go anywhere from here. In order to finish the reaction, your solvent that attaches needs to be protic to finalize the reaction. Does that make sense? We're going to see that again. We're going to see that again in 2 chapters when we do chapter 7.
What happens to the ROH that picks up the hydrogen?
The ROH that picks up the hydrogen, very good question, becomes ROH2 plus and floats around the flask as an acid.
And the water doesn't just break off?
Huh?
And like a water group doesn't just break off?
If you broke off the water group, you would leave behind R plus. And remember, that's just another carbocation. Why would you produce a carbocation when the positive charge can just sit on the oxygen and they both have their octet? We'll look at that in a second, don't worry. Okay. And also, forming that acid isn't really a problem here because this whole thing is acidic because the carbocation, right? The carbocation in and of itself is acidic, right? What type of acid is it? Lewis or Bronsted? Does it have any protons that's giving away? It means it's not Bronsted, right? It means it's Lewis because a Lewis acid is deficient in electrons. Very good. Okay. So that whole thing is acidic in and of itself. So this is the amphiprotic nature of an alcohol, correct? And I want you to know that alcohols have a pKa when they give off their hydrogens. And their pKa is anywhere from 16 to 18. Was anyone here at my Orgo review the other day? That's okay.
You changed dates.
I do. I did. We're going to do a lecture here soon that's very highly requested. We're going to do the whole metabolic map. Put it on YouTube. Because no one does the metabolic map properly. I'm talking to all of you out there who teach the metabolic map. Y'all are all doing it wrong. I'm kidding. You guys are great. No. Like they do it well. I just do it better. The only exception here that you would need to know is something like this. Why is this an exception? The pKa here, I think, is like 10.1. Why is it so much of a stronger acid? Why is it 10 to the 6 times stronger than the next strongest alcohol? Yeah, so we have to judge acid strength, remember, based on the stability of the conjugate base, right? I have to make a video about that very soon as well. We have to judge acid strength based on the stability of the conjugate base, correct? So one of the things that stabilizes the conjugate base, let's deprotonate this guy. And when we deprotonate it, we're going to get O minus. But that O minus is next to an entire system of conjugated p orbitals. So these electrons are going to resonate, and then they're going to resonate and go back and forth, blah, 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 and they're going to spin around in an aromatic fashion. So flip and flip and flip and flip, and that delocalization of the negative charge induces a stabilizing effect that distributes the negative charge throughout the molecule. And since that's not a localized charge, which we don't like, the delocalization of that charge actually benefits the molecule. Did you guys watch my resonance video that I told you guys to watch on YouTube? You need to know that video by heart. I have a resonance lecture on YouTube. It's literally like, look on my channel, look up Yusuf A. Hassan, Look up resonance, and it'll show up. It's like an hour, 15-minute long lecture. It's like the gold standard for understanding how things like this work. Not saying that it's like a fantastic lecture or anything. I think it's okay. I don't think it's one of the best lectures I've ever given because it's so abstract. Like, and I'm building up from like somewhere that you might not even meet me at, but it's very beneficial. I still think so. Anyone watch it here? Did you like it?
Yeah, I liked
Good. Okay, so that's why the pKa is so much lower over there, right? So this is a really good backbone to understand why alcohols do what they do, right? And I like to really sort of harp in on that because of the fact that we immediately go into reactions with alcohols. There are some reactions that you just have to memorize, and there are some reactions that we are going to sit here and diligently explain. One of the reactions that you just need to memorize is the fact that when you oxidize an alcohol, you are going to get a carbonyl, right? If you take a primary alcohol meaning it exists on a carbon that is connected to one other thing, whereas a secondary alcohol would be a carbon that's connected to two other things, and a tertiary alcohol would be something like this. There's no such thing as a quaternary alcohol, right? If you oxidize a primary alcohol all the way, the oxidizing agent is known as Jones reagent. You will identify it through the recognition of chromate and some sort of acid, chromium and some sort of acid. So sometimes you'll see it as just chromic acid, H2Cr4O7 or something like that, whatever it is. It's H plus and chromate. I forgot exactly what it is. And you will see it just written as Jones. Jones reagent will take a primary alcohol and oxidize it all the way up to a carboxylic acid. What's actually happening here? What's actually happening is that each of these hydrogens are getting stolen away and the electrons are falling into the bond. And then another one of those hydrogens getting taken and swapped for an oxygen on the molecule, right? That's going to create a carboxylic acid. Yes? Jones reagent. And it's going to look like some form of chromic acid. CrOH, I don't even know if this is correct, but I think it's like Cr2O7, something like that, right? Someone look it up. Someone look up what Jones reagent is. I don't know. I don't want to get this wrong. Yeah, this is so beyond me. Can a secondary alcohol turn into a carboxylic acid? No, because you need the availability of that second hydrogen there. You need to be a terminal group, right? So this guy only has one hydrogen to take right here. So when you oxidize that, what is that going to turn into? It's going to turn into a ketone. Once again, hydrogen is going to drop off its electrons. Hydrogen gets ripped off, and you can see the double bond forming with these electrons right here, right? You guys get that? The tertiary alcohol will be oxidized into what? Huh? Can you do this? No. It's not going to do anything. You can't oxidize tertiary alcohol. There's no hydrogens to take. That's correct. H2Cr2O7.
Some of them use Na2Cr2O7.
That's fine. Yeah, that's the conjugate base.
Where does the second oxygen come from for the primary alcohol?
It comes from the Jones reagent itself. Yeah, I believe. You don't really need to know the mechanism. Now, the question in all of your heads should be, if the ketone comes from the secondary alcohol, then the aldehyde must come from the... Where does the aldehyde come from? If the ketone comes from the secondary alcohol, the aldehyde must come from the primary alcohol. How do we get the primary alcohol to turn into an aldehyde without making it a carboxylic acid? What's the name of the reagent? Pyridinium chlorochromate, something like that, right? PCC, but otherwise known as what? What do I call it in my lecture video? Please create carbonyl. Not carboxylic acid. Please create carbonyl. It will turn this into a carbonyl. It is a poisoned version of Jones reagent. You poison the Jones reagent, I think, with like a little bit of lead or something like that, and then, I don't know, it's something, whatever. I took orgo so long ago, and you don't need to know it either. But it's Jones reagent that stops at the aldehyde. I feel like I never left.
How was the weather swap?
Huh?
How was the weather swap from New York?
The weather in New York, I think it was like 20 degrees every day when I was there. 20, 25 degrees. I came back here and I was like, wow, I am sweating. I was also sick in New York for a few days. What's funny is my entire house got, I believe is a very bad case of the flu. I think everyone got a really, really bad case of flu. And somehow I escaped it for a while. Then I went to my PCP to go get my like cholesterol and blood checked and everything like that because like I had a bad report like 2 years ago, and then alhamdulillah everything's better. Just been like losing weight because I'm not in medical school anymore. And I went to my PCP and he was like, "Do you want your flu shot? Like it's still in season." I was like, "Yeah, of course I want my flu shot." So I got my flu shot, and then legitimately like 4 days after I got my flu shot, I was like, wow, I'm like feeling a little hot and like kind of gross. And usually like everyone's like, oh, well, you just got the shot. Of course you feel sick. But that prodromal symptom is supposed to happen in like 24 hours. And then I was sick for like 3 days, but I was really mildly sick. And I had like all the flu symptoms. And I was like, wow, if I didn't get the flu shot that day, I probably would have been like on my ass, like totally out of it. But I got lucky. Blessed. Okay. So that is oxidations of alcohols, right? That's oxidation with Jones reagent. But there's another thing we sort of have to look at over here, and it's the fact that other than doing oxidations, we can also do dehydrations of alcohols. Dehydrating an alcohol is something the MCAT asks you all the time, right? And there's a certain series of questions that you need to be able to answer about dehydrating any alcohol. So the first of these elusive questions about dehydrating alcohols is number 1, can it happen? Does this show up on screen well? No? Okay. So number 1 is, can it happen? Number 2 is it fast? And more so, they're asking, is it faster than something else? And number 3, mechanism. These are the 3 questions you're going to need to answer about alcohol dehydrations. We're going to go step by step, one by one, and cover each and every single one. We'll start with primaries, secondaries, tertiaries, and we'll talk a little bit about resonance stabilized alcohols. Let's do a primary alcohol. Every alcohol dehydration that you're going to see on the MCAT, almost every single one, is acid catalyzed, right? We're going to use a tiny bit of a catalytic amount of H2SO4, a catalytic amount. That's why it says cat, right? H2SO4 cat, right? And that's kind of it. Once you put that, it's going to begin. You want the reaction to go a little faster, you heat it a little bit. You put a little fire under there, right? What's going to happen is that the H2SO4, or whatever acid you really put in, it doesn't matter, to be honest. The H2SO4 is going to pick up, get its hydrogen picked up like that. And we're going to make a protonated version of the alcohol. I want to write it like that just to show you that that group is actually prone to leaving. Right? I don't want to draw it out like the deprotonation alcohol. If I wanted to show you that I wanted to be deprotonated, I would have written it like this, right? But I want you to sort of look at that as a leaving group because you know when that leaves, what's it going to make? H2O, right? So now we got that, and we've got HSO4 minus, which will or will not participate in the rest of the reaction. Will not, because it is the conjugate base of what? A strong acid. The conjugate base of a strong acid will no longer participate in the reaction as a spectator ion now, right? This guy. Here's the thing. I told you that we're going to get some sort of process of removal. This becomes a leaving group. Can this guy leave by itself? Why not? Because if you do that, we're going to form a primary carbocation. Not likely at all. This is why I hate it when people say, I say it sometimes, but like I also make a caveat. The MCAT doesn't test elimination anymore. They do. It's hidden in the details. This undergoes what's called an E2 elimination, a bimolecular elimination, meaning that you have a molecule with a leaving group that gets its leaving group eliminated by a second molecule. And what you need to know is that there's a hydrogen right here. And you realize that the positive charge, that's a withdrawing group, right? Basically taking the positive charge, calls the electron, says come here, come this way, right? So as we do that, we see the polarizing nature of that bond. And the polarizing nature of that bond is going to pull this way, and we're going to get a partial positive charge right here, correct? That partial positive charge is now going to do what? Pull on the rest of the molecule. This is called induction. This is the inductive effect. It's going to pull slightly less, but we're still going to pull, and we're going to get a slightly positive charge right here. And now that slight positive charge is going to pull on the bond to the hydrogen. And it's going to weaken the bond that that hydrogen has there. So this hydrogen is ready to be taken. The reason I'm showing you this is because later in chapter 7, when we do enolates, we're going to see the same thing. Same exact thing, right? Where the positive charge pulls electron densities all the way up the end of the molecule and leaves the hydrogen ready to be taken. But we're going to see a completely different mechanism, right? So if you can imagine that hydrogen, the bond is actually weakened by the fact that there is a nearby positive charge. So what we can have actually, remember I said that alcohols are amphiprotic. This one picked up the proton, that one's gonna take the proton, right? And then kick off. Well, they're both taking protons, I guess. So, boom, I guess this is an example of amphiprotic, I misspoke. They can pick up protons, right? So this one's gonna pick up the proton. Boom, these electrons are gonna go where? Into the molecule. And this is called assisted leaving, where the moving of electrons into that sigma bond creates a pi bond that kicks off the leaving group. 3 steps. Boom, boom, boom. H gets picked up, drops off its electrons as it's saying goodbye. It leaves without its electrons. Electrons move into the sigma bond, making a pi bond between the 2 carbons, kicking off the leaving group. And as we do that, we get a double bond, which is always the final outcome of an alcohol dehydration. And we also get a molecule of protonated alcohol. But do you see how that protonated alcohol is the same as this, right? So basically what we did is that the final step of the reaction recreated the intermediate. What is that called? A catalyzed reaction. Remember how I said there's a catalytic amount? Because this and HSO4 minus is the same thing as having this and H2SO4. Do you see how we haven't changed from the beginning? That's called catalysis. The fact that the end products and whatever else you make help to form this thing again. They go back and they form this again and again and again. Because now all you need to produce this is that and another molecule of alcohol. And then that's going to turn into this and another molecule of alcohol. You're going to keep going and going and going until you have no more molecules of alcohol to go. Does that make sense? Which is why you guys did Orgo Lab on campus. You had a whole flask full of alcohol. You put a slight fire under it, and you add like a drop of sulfuric acid. That's it. That's all you need, because it kicks off by itself. That's a catalyzed reaction. A lot of the reactions we're going to see are catalyzed because of the fact that the alcohol can pick up and drop off protons. It's a carrier of the proton, basically. You were asking a question earlier where you said, why can't this, what's going to happen to that? It's just going to float around. It's fine. It's happy like that. It's okay. Right? But you're also saying, why doesn't this just leave? Well, it doesn't leave for the same reason that that didn't leave over there. Because you're going to make a carbocation. I know that it looks tempting to do this. Just do that. You have water. And you could do this if you had a double bond here because now it's stabilized. But remember what I said. When carbon is positive, it does or does not have its octet. It does not. That's six electrons, right? But look at this. Let's do this empirically, the way that we never do in organic chemistry, but it'll be easier to see. Bless you. Even with the oxygen being positive, everyone still has their octet. What's more important, respecting the electronegativity or having everyone be stable in general? Having everyone be stable is much more important, which is why this is okay, and that's not. That's not okay. That makes sense? You remember the example of the pinnacle rearrangement that we talked about, where the oxygen fronts the discomfort of the carbon? We had that whole methyl shift, and I was like, why is a tertiary carbocation turning into a secondary one with withdrawing? Well, it's because of the resonance. The resonance contributor stabilized the octet of the carbon, right? We're going to see the same thing later. But later, in enolates, instead of fronting a positive charge, the oxygen fronts the negative charge, which makes more sense. That one makes a little more sense. You guys get that?
Can you run through that one more time?
Which part?
Most of the beginning, just like the beginning part before you went into the whole reaction.
Over here?
Yeah.
Yeah, so basically you have an alcohol, right? You have sulfuric acid. That sulfuric acid is able to protonate the alcohol because of its nature, right? That protonated alcohol, basically what can happen is that you're trying to take this group and remove it from the molecule. It can't leave by itself because it leaves behind a primary carbocation in its wake. By leaving behind a primary carbocation, that's incredibly destabilizing. We would rather just keep the positive charge on the oxygen. But what happens is that another alcohol molecule, because of the induction and the weakening of the carbon to hydrogen bond at this terminal of the molecule, picks up the hydrogen, drops off the electrons, kicks off the group, and makes a double bond. This is the product. This is literally the product. I don't want you guys to not see that. That's the product.
So it's taking the hydrogen from that alcohol on the bottom?
Yes. So basically, this is the functional group. This is the alpha carbon. It's taking the hydrogen from the alpha carbon. I think it'll be a little easier to see. Like, it's kind of hard to see when you do it with 2 carbons. I do that for a reason. But let's just try it with like a larger amount of carbons, right? Let's do it like this. Yeah? I'm just going to say H+. Protonation gives you. And then, from here, makes sense. Right? We had a 4-carbon alcohol. Remember, that's not 5 carbons. You are so tempted to say that's 5 carbons. So tempted. But it's 4 carbons and a bond to a hydroxide group. Primary alcohols are hard to see. I struggled with them for a long time before I really understood why they're drawn like that. Yes?
So the second alcohol group is just floating around in excess?
This?
No, like the bottom one.
This one?
Yeah.
That's the solvent. And not even the solvent, it's also the reagent. This is one example where the solvent is the reagent is part of the product.
Dumb question, but like the hydrogen in the middle bottom?
Guys, this is going to happen a lot. The Aldol reaction that we're going to see in chapter 7, all you need is an aldehyde. That's it. That you need an aldehyde and a drop of base. You're done. This is just alcohol and a drop of acid. Done. Yes?
Just so I think I'm going well. Like the hydrogen over there, like where did that come from?
It's on the molecule.
Okay.
Yeah. This isn't the acid hydrogen. This is the acid hydrogen right here.
Oh, okay.
This is the hydrogen that's in the carbon backbone. Right? Because if we were to draw this out empirically, we would actually draw the hydrogens right here.
Oh, okay.
Those are the hydrogens right there. Right? Make sense? You guys doing okay? I get so scared when people just start like asking one another things because I was like, what if they're wrong? Secondary. Oh, right. Let's go through these. Can it happen? We went over, right? It can happen, but it happens through an E2 mechanism. So let's draw a little chart. You guys like charts? Primary, secondary, tertiary. Can it happen? Yes. Happens? Yes. What makes it fast? It's actually the ease of removal of the alpha hydrogen. The ease of removal of the alpha hydrogen will make it faster than anything else. So if we had something like this that was going to get dehydrated versus something like this. that was going to get dehydrated. Why is this going to be faster? Well, when we want to remove this hydrogen right here, it's actually compounded with a withdrawing group. You guys see how this is going to withdraw and withdraw, so the hydrogen gets withdrawn from, so the hydrogen is going to be easier to take, right? You might not get questions like that, but you will definitely be asked this question about the secondary and tertiary. Funny thing is, it's much easier to answer those questions for those. Yes?
Is heat making the hydrogen easier?
Huh?
You said earlier that heat would make the reaction proceed faster.
Right. I said that heat will make the reaction proceed faster. Heat makes all eliminations happen faster. It's not because of the bond stability, it's just all eliminations happen faster with heat. And when you're doing a substitution reaction that has a side profile of elimination, increasing the heat will increase the proportion of elimination that happens. Yes?
So you mentioned that it was an E2 mechanism.
Mhm.
But with an E2 mechanism, don't you need like a strong base? And if you use like H2SO4,
E2-like mechanism. E2, yes, is normally an elimination with a base. But if you think about it, in these acidic conditions, the deprotonated alcohol is acting as the base. You get it? This is the pattern recognition thing I was talking about. You need to recognize that this what you need to recognize is that this is the same thing as this. Those are the same. One's basic, one's acidic. Done. Those are the same thing. Can you guys see it? Look, all you did was replace the Br with an OH. That's it. And you made it acidic. Oh. Primaries, done. Secondaries. Oh, I'm so excited to do the carbonyl chapter. Because if you guys understand this, you're really, really going to understand carbonyls well. Oh, last thing, mechanism. E2 in acidic conditions. Let me tell you something real quick. In acidic conditions, things that are neutral become bases. Because the nucleophilicity and electrophilicity are relative to what's in the flask. If you have sulfuric acid in the flask, can it get deprotonated by nitric acid? Sulfuric acid is stronger than nitric acid. Will it get deprotonated by nitric acid? Yes, and this is actually a very common reaction. Sulfuric acid can be deprotonated by nitric acid. And it will make, does any orgo whiz remember when you do this? It'll make that. And then what happens is that these electrons move in this way and you'll make this. Does anyone know what this is important for? When you do electrophilic aromatic substitution. To make the nitro group that's going to attach onto the benzene ring, you need to mix sulfuric and nitric acid. The actual mechanism is that sulfuric acid, one of the strongest acids in the world, is protonating nitric acid, another one of the strongest acids in the world. Do you see how nitric acid is a nucleophile, even though it's an acid? Nucleophilicity is relative. It's not a permanent concept. In the presence of sulfuric acid, nitric acid is shy. Right? In front of you guys, I am very different than I am in front of just Hamza. Right? Hamza? Can you verify that statement? Yeah. Right? It's all dependent upon your environment.
What does that say under what makes it fast?
Ease of removal of the alpha hydrogen. Let's look at the secondary mechanism. A secondary alcohol, do you guys remember how we had this right here and it turned into a double bond like that? Do you see how the double bond goes towards the alcohol? You'll actually be able to see that with a secondary alcohol, if I said dehydrogenate that, dehydrate that, you just drop the double bond. If you wanted to know what the product was, drop it towards the alcohol, right? From the alpha carbon. Secondary alcohols. Something like this. Add a little bit of acid, right? Protonation of the alcohol will give you the leaving group. The leaving group can leave. What is this looking like now? It looks like an SN1E1 reaction, right? That carbocation is going to induce and weaken the bonds to the hydrogens on both sides. Alcohol in excess, also the reagent, will deprotonate. We get a double bond and catalysis. Make sense? What will make this faster? It's no longer the speed at which you remove the hydrogen. It's the speed at which you make the, What's the most unstable thing here? The carbocation. If the carbocation was more stable, would this happen faster? Yes, it's carbocation stability. The mechanism here, if E2 was like SN2, this is like SN1, so this is called E2 is like SN2. This is like SN1, so this is called E1. Unimolecular elimination. Goes through a carbocation mechanism. Some considerations, okay? There are some considerations with secondary alcohol dehydration. Protonate. Where am I going to deprotonate from? HA or HB? Huh? HA or HB? HB, why? Huh? Well, oh, sorry, I haven't made my carbocation yet. Oops, stupid. All right. Once again, HA or HB. You guys said HB, why? It's more stable, why? More substituted. We want the double bond to be as substituted as possible. So if we drop the double bond this way, it only has one thing attached to it. But if we drop the double bond this way, it has two things attached to it. Right? Is that the only product we're going to get? We're also going to get the cis product. Remember, free rotation about the bond means that this thing is spinning. And you might not deprotonate it like that. You might deprotonate it when it's caught like this. So this is the major contributor, as it's most stable. And if you want to know why that's stable, it's called hyperconjugation, right? These methyl groups donate a little bit of electron density into the p orbitals of the double bond, right? Because of their parallel nature. This will be the minor contributor, or the minor product. And this will be an incredibly minor, almost negligible product. That won't really happen. Understood? Happens? Yes. So a question you will often get on the MCAT is, between this and this, which one will undergo a dehydration faster? Instead of sitting there scratching your heads thinking about it, why don't you just put them in the flask? Why don't you just make these two do the elimination? Or sorry, you make them do the dehydration. Remember, I said the one that's faster is the one that's more stable. Which of these is more stable? Top or bottom? Bottom? Yeah? Why? Inductive effect. We have induction and we have induction. Except every single one of you is wrong. Because it's a carbocation, not a negative charge. You withdraw from negative charges. You don't steal from the poor. This guy is poor. This is electron poor. Why are you taking electrons away from that which is already electron poor? Now this isn't a plus 1 charge. This is like a plus 1.3 charge. And that's a plus 1. Remember, we want to take away from a carbanion or a negative group. If we take away from a negative, that stabilizes it, which is why I said the inductive effect is one of the 5 effects that stabilizes a conjugate base, which is negative. If it's positive, this is destabilizing. You have to flip your logic. This is going to dehydrate faster because the carbocation is more stable. Understood? Tertiary. Same thing as secondary. Literally. Protonate. Leave. Take from any of these. And you get double bond. Carbocation stability. E1. Yes. Can I dehydrate this? No, there's no alpha hydrogen. It doesn't exist. Right? Let's do an example. Someone want to come up and dehydrate that for me? Or do you want to tell me how to do it? Tell me how to do it. How am I going to do this?
You're gonna, like, which hydrogens you're gonna take at the end?
What do I do first?
Protonate.
Protonate, the alcohol. Now what?
Another one of your same substrate is gonna come in.
Will it? I mean, you could, but normally with a secondary alcohol, we use a carbocation.
So then it's just gonna pop up.
So make the carbocation, right? Honestly, secondaries can go either way. So like, we don't really talk about that, but they can go either way.
So it's otherwise it's just gonna pop off as a water.
Yes.
You're gonna get a carbocation, and it's gonna go that way. So you have.
You know, this way.
So you have 3 substitutes.
Okay, so I am going to take this with another molecule of the alcohol, and I'll have 3 substituents. So close. But you're wrong. You're wrong about your mechanism. This is technically the product, but your mechanism neglects the fact that more than likely, when forming this carbocation, it's actually going to hop ship because there's a tertiary position next to it. And then we eliminate from the opposite direction. It doesn't change the product, but the mechanism is different.
It's just a hydrogen.
Doesn't change the product, but the mechanism is different through a hydride shift
Why would you do a hydrogen?
to make a tertiary carbocation.
It's
Every single time you make a carbocation, remember what I said in the other lecture before break? Every time you make a carbocation, you need to look and see if you can make a more stable one. Tertiary is more stable than secondary. Has to happen. Even if it doesn't change the product. Because what? The carbocation doesn't know what the product's going to be. It just knows, hey, next door over looks pretty nice, right? That makes sense? Sometimes it will change the product. Sometimes it will. Does that make sense? Good. I want to talk about resonant alcohols, but they sort of follow the same rules. So, no big deal. Everyone okay with that? Any questions? Comments, concerns, grievances, complaints? Anything else I should know about? Yes?
Question. So for heading on slowly, while you said like be aware of hydration and mental shifts, how often do you see ring expansion? Like is that common to have to do?
I think I've seen a ring closure one time on the MCAT, but not an expansion. Okay. There's one more thing. You need to know how to turn an alcohol into a leaving group. There's two ways to do this. The MCAT only really tests one. This reaction is known as, you have a red marker?
This is green. So no.
This is like my worst nightmare.
I think that red one actually works now.
No, it sucks.
Yeah.
Tosylate formation.
That one does.
I thought you were like messing with me because that was a red cap. I'll take that from you. Thank you. Tosylate formation. You know, the other day I got an email that someone said they're like from another town over in Texas, like somewhere like far away, and they're like, I want to come to Dallas with a friend to see you teach. And I was like, why? Why would you do that to yourself? It's like, oh my God, guys. Qalam, VRIC, talking tacos, like all the great food in Dallas, see all my friends, and organic chemistry lecture. Let's go. You're like, what? Ditch the coffee shop, man. Come to Orgo. You like walk in, every single inch of this wall is painted in biochemistry. Or step right out. I would dip. Are you kidding? I would never set foot in this school. I'd probably drop out of college. I would leave. My biggest fear is that one day, like some freshman year pre-med is gonna like waltz into this room and I'm just gonna be like shouting at you guys with like all this stuff behind my back. And you're like, nope, not for me. I'm done.
Learn what a valence electron.
Literally. They like literally just memorized what carbon's like atomic weight is, and they see like PFK2 fructose 2,6 bisphosphatase, like fed and fasted state interactions.
This reminds me of the freshmen who were asking me, do you think I should come to Yusuf's class?
No. If anyone here is under the age of 20, get the hell out of this room. Like, I know one of you is. I forgot which one. They're like, wow, you guys are awful friends. What the hell? Like, what do you mean? You don't know? Okay, tosylate formation. This is how you turn an alcohol into, I will make the caveat because it's taught in organic chemistry, so you turn an alcohol into a same side leaving group. A leaving group on the same side. What I mean by that is that if you begin with a, wow, this is a very bold red marker. If you begin with a alcohol on this side, the leaving group is going to end up on that side. And the leaving group is going to be written as OTS, oats, right? Oats is a very good leaving group, right? The actual molecule that forms the tosylate is called tosyl chloride. You begin with TSCl, right? And you put a little bit of pyridine inside of this. A little bit of pyridine in that flask. What happens is that TSCl looks like this. Oops. That's TSCl. The sulfur in TSCl has what geometry? What electron geometry? Huh? Tetrahedral. Why? Has 4 domains, right? 4 domains means tetrahedral. Why is it allowed to expand its octet? It's a period 3 element. Don't tell me it can access the d orbital. I know that. I know that. I want you to tell me why. Why can it do that? Because the d orbital doesn't appear until period 3. And sulfur is a period 3 element. Remember the part of the periodic table we need to memorize? We have boron, carbon, nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, silicon, aluminum, bromine, iodine. Up here is helium, and all the way over here is hydrogen. And I would also like sort of know like lithium, potassium, sodium, just so that. Huh.
You might have said this before, but why do we have to memorize it if we already have access to periodic table data?
Because do you want to waste the couple seconds looking all this up when you could just have it in your head? While you're wasting those seconds, another guy's going home, driving in his car, happy with his 508 that he just got. But you are looking up the periodic table.
472 inbound.
472 inbound. Please don't get a 508 on the MCAT. Please do not struggle and strive and I don't mean to be condescending. I'm saying this with a very open heart. I understand the MCAT's a ridiculously difficult test and everyone has different life circumstances. But do not make I don't want to see any more emails where people are like, I need your help studying for the MCAT. All I need is a 508. Don't do that. You are performing a disservice to yourself and the rest of this community. There are people legitimately bending over backwards, breaking their backs, working full-time, studying, not seeing their families, separated from their children, studying for this test, just keeling over, trying to get the best score possible. And you're sitting here in front of someone who wants you to get the best score possible saying, all I need is this. That is a very reductive mentality. It's not going to get you very far. So yes, if you struggled and strived and you did this and you did that and it got you such and such far, be very proud of the work that you did. But don't be proud settling for less. Don't plan for anything, to be honest. Plan to do the best. Because if you're not planning to do the best, what are you doing here? Why are you here? Why are you learning? What are you studying for? For mediocrity? Why? What's the point? What's the point of living a mediocre life? You know? And everyone's like, oh my God, that's so dramatic, blah, blah, blah. No, this is your life. You're a student. Put your whole heart into it. Anyways, tetrahedral geometry means that we can actually do some chemistry on it like what we do to carbon, right? Meaning that if I were to take a nucleophile, like an OH, and approach it like this, I can actually attack it and in some interesting way, kick off that chlorine. You guys see that? The electrons go up after it gets attacked, comes down, and then moves out. I can show you the whole middle ground. Do you guys want to see how it looks in the middle? Okay, the middle ground is going to be something like this. So I'm just going to do ROH, right? The O is going to catch a positive charge. It's going to connect to the S. The S connects to the electrons we just kicked up, another oxygen like this, a chlorine like this, and then the benzene ring over here. And now these electrons are going to come down and kick off that chlorine. I'm showing all of this in one shot. Or no. Sorry. You guys get that? So we're going through an oxide intermediate and coming back down. What time is it? Wow. Oh my God. Just really hope we set up well for the Carbonyl chapter. Because Aldol's going to take a second. All right. After we kick that off, we're going to get, stick with me now, yeah? That little bit of pyridinium is going to come and take that. Do you see how this end of the molecule that the O is attached to is just this without the Cl? You take this, look, let me show you the original molecule. Do you see how the oxygen is attached to this without the Cl? You replace the Cl with the oxygen and the alcohol. Remember we call this TsCl? So this whole thing is called Ts. And these are equal. That thing, this whole thing is a really good leaving group. Can someone tell me why? Because when you kick it off, what do you get? A negative oxygen that resonates into the sulfur and the oxides. Right? Does it resonate into the benzene ring? How do you check? How do you check to see if this resonates into the benzene ring? Well, we have a p orbital here, and here, and here. Is it connected to the p orbital here? Yeah, it is. So you could. Can you, though? Let's take a look. Let's take these electrons, move them here. And then we take these electrons and move them here. Then take these electrons and move them here. So you could, well, you're just trading off the negatives inside of here. You're just doing that for no reason, really. Right? Because now instead of two, because that's going to become like that and that. And now this gets like a positive charge, whatever it is. I don't know. I don't know if you can. To this day, I don't know the answer to that question. It looks like you can. I don't know if you really can. You have to break off the double bond upwards, form another one going sideways. Stupid. No point, you know? But that's a really good leaving group because of the fact that once you kick that off, once you get that, you get oxygen. What I do know for sure is that the oxygen will resonate up to these two oxygen points, giving all of these the shared responsibility of carrying that negative charge. The MCAT really loves to harp on one question about tosylates. And the question is, in tosylate formation, what is the first atom that's attacked? What's the answer? Sulfur. Who's seen that question before? I've seen it a bunch of times. I don't know why. I don't know why they harp on that so much. I just want someone to punch me in the face. Aldehydes, ketones. Moving on to chapter 6. We have already spoken about the fact that aldehydes and ketones are oxidations of alcohols. That the primary alcohol will oxidize to the aldehyde, if not to the carboxylic acid, and the secondary alcohol will oxidize to the ketone. Aldehyde and ketone chemistry is interesting. And this is the diagram I drew for my student yesterday that I will now teach you guys. This is the anatomy of a ketone. And you can also say of an aldehyde. It doesn't really matter what's, I'm just going to say R and R. You know, I'm going to leave this off for a moment. This is the anatomy of a aldehyde or a ketone, correct? The R prime, if the R is a hydrogen, then that's an aldehyde, correct? Okay. The oxygen is doing what to the electron density of the carbon? It is withdrawing, right? So number one, do you guys like when I explain every part of the molecule? Is that helpful? Number one, it's polar. So that means that this is slightly negative and this right here is slightly positive. Correct? That slight negative along with those electron pairs makes this a very good what? Makes it a very good Lewis base. Number two, the carbonyl oxygen is a good Lewis base. And by good, I mean it participates like that often. Not that, oh, it's so basic. You know what I mean? But it can pick up a hydrogen. I guess it's a Bronsted base, right? I guess you could say both, a Lewis or a Bronsted base. Because the Lewis base, because of the electron density and its ability to sort of donate in. You could make an argument for either one. But also, we have p orbitals, right? So the next thing is that it is trigonal planar. I'm going to leave some space right here. The fourth thing is that because of the partial positive charge on the carbon here, the carbonyl carbon has a p orbital and a partial positive charge. The carbonyl carbon is a good what? Huh? Good electrophile, also known as a Lewis acid. Meaning it can be attacked by a nucleophile. And because of the partial positive charge here, do you see how we're inducing up the molecule? Remember, I told you this would come back. We're inducing up the molecule, which means that the hydrogen right here, number 5, the alpha hydrogen is labile meaning free, for removal. 5 things you need to know about carbonyls. Remember that the carbonyl is just the carbon double bonded to the oxygen. That's what we mean by carbonyl. So aldehydes and ketones, they're both carbonyls. Formed from the oxidation of alcohols. There's 2 main mechanisms and reactions you need to know about. You have hydrations. Let's do a ketone hydration. You will put this in a solution of acidified water. And the hydrogen of the H3O plus will be picked up by what? What's the base here? I remember, oh my God, I just got traumatized. I remember it so clearly. Professor Merlitsky, every single time we were studying carbonyls, what's the first thing he said? What's the first thing you do? Protonate the carbonyl. Protonate the carbonyl. Protonate it over and over and over and over again. Protonate the carbonyl. Burn it into your head. When there's an acid near a carbonyl, protonate the carbonyl. Protonation. Bronsted from these electron densities right here. Protonation of the carbonyl leads to the formation of a positive oxygen, which even more so withdraws the electron density than it was already being done from the carbon, making the carbon site even more what? Huh? What you said. Electrophilic, making it even more electrophilic. Now we have water floating around in a flask with a very electrophilic position. What's the water going to do? Attack as a nucleophile. Yeah? This is the water we just attacked with. That used to be the carbonyl. See how that popped up? And now what do we do with the water? We deprotonate. And this is called a hydrate. A hydrate, also known as remember last chapter, a geminal diol. A hydrate, also known as a geminal diol. And considering you have the geminal diol, you can also see how naturally you can actually reverse this whole process. You can take the geminal diol protonate one of the alcohols, move its electrons back down off the molecule from the carbonyl. You see that OH on the left? I'm sitting in the back of the room. I just want to see what it looks like. You see that OH on the left? It can resonate down its electrons to kick off the protonated water molecule, and then you can deprotonate from the back. And you can get this whole thing in reverse and reform the ketone. I'm a little congested, I apologize. Any questions?
So that OH, okay, it's like the water you added, right? Why doesn't it just leave off?
Why doesn't it just leave?
Yeah.
Because you just go backwards. There's two reasons that doesn't leave. Number one, you're talking about this, right?
Yeah.
Yeah, same question as she does. This doesn't leave for two reasons. Number one, if this leaves, you're just going to get this. And that's going to turn into that. You're just going to go backwards. Right? And the second reason is you have to move forward in the reaction. So it can be deprotonated by the solvent, so it'll just do that. So hydrates, also known as geminal diols. Same thing can happen with an aldehyde. You guys want to know a funny trick? Who here is writing on an iPad? Take your whole thing, lasso it, copy it, and drop a hydrogen right here. That's it. Same thing. That is called a hydration. The aldehyde hydrate and the ketone hydrate, both known as geminal diols. Next one, we're going to spend a little bit of time on because this is another lesson that I gave very recently and something that I really love to harp on to make things a little more clear to my biochemistry people. Who here actually likes biochemistry? Do you guys like how it works, how it looks? You guys are going to love this next part of the lesson. All right. I'm going to keep this. I think it's important to look at the anatomy while we do this, right? Huh? Alpha hydrogen is labile for removal. Right? What's more electrophilic, the aldehyde or the ketone? Let's go back to our basics of chemistry. Let's look at the ketone. Let's look at the aldehyde. We know that the oxygen is withdrawing the carbon's electron density. These methyl groups, are they donating or withdrawing? They're donating. So you're donating to the thing that's getting withdrawn from. Is that good or bad? That's good. Because this guy's getting stolen from. You're giving him money, giving him electrons, right? This guy only has one. So the aldehyde is more electrophilic. This is called hemiacetal and acetal formation. Do you guys remember how in the alcohol chapter I told you alcohols act a lot like water, except you replace the H with an R. Do you guys remember how just when we did the hydrates, we said that this right here was the one that we added, right? Take that H and replace it with an R, and now you have what we're going to do. Okay? Let's take a look. Hemiacetal, acetal. It says acetal, so we're going to begin with a aldehyde. Technically, when you do it with a ketone, it's called a hemiketal and a ketal, technically. Let's do it with an aldehyde. First thing you do is what? Someone did say deprotonate? Get out. Get out. We're going to protonate. We're going to protonate what? The carbonyl. Protonate the carbonyl. Oh my God, I already messed up. Hold on. Sorry, guys. It's ROH. So we're going to have ROH. H plus. Take this, take that. We get this. And then we have alcohol left behind. I told you, alcohol will do everything that the water does. What did the water do here? It attacked. Like this, right? OH, O, H, and what else? R. Now what's going to happen? Now we're going to deprotonate with what? The alcohol. Or if you want to show the catalysis of the reaction, you could be cool and nifty. You could deprotonate with the ketone or the aldehyde. But don't do that because technically the solvent is in excess of the reagent, so the solvent's going to do the deprotonation. This is going to form something known as the hemiacetal. Why is it called a hemiacetal? Half of it is OR and half of it is OH. This is the hemiacetal. Okay. Can everyone please just close their iPad, stop writing, don't take notes, blah, blah, blah. You know the drill, right? Okay. Huh? Hold on. Just wait. Hold your horses. Gonna get rid of the anatomy. We've been looking at this for long enough. Okay. What happens if, let's say by some crazy idea, you made a molecule like this? Yeah? You made a molecule like that. Do you know what's coming?
Yeah.
Okay. You made a molecule like this and you threw it in a vat of acid. You're going to protonate the carbonyl. And then obviously another molecule like this is going to come and do that, right? And then what's going to happen, blah, 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 you're going to go step by step by step. You're going to get this. Something like that, right? Is that actually what happens? No. Why? Yes, because we have a member of the molecule that is capable of attacking. This guy can attack there, right? 1, 2, 3, 4, 5, 6-membered ring will form. Okay? Stay with me. Everyone just stare at the board. Hey. You too. I don't care. Tell her I don't care.
Okay.
This guy hits there. Kicks up. 1, 2, 3, 4, 5, 6-membered ring. On the 1 carbon is the 6 OH. On the 1 carbon also is the, actually, yeah, let's do it like that. On the 1 carbon is the 6 OH. On the 1 carbon is also the OH you just kicked off. We also connected 2, 3, 4, 5, 6. 6-membered ring. Yes? Makes sense. You guys get how we got here? What is this? Where's the hydrogen going to be? This 1 carbon has a hydrogen on it. This OH used to be the aldehyde, and this guy still has a hydrogen on it. Right? That's the O that attacked. You guys see? This chain, if we trace it this way, is the same as going this way in the ring. You guys see that? Can you guys visualize that? Can anyone not see it? Okay. Cool. Oh, crap. I shouldn't have erased that. Okay, hold on. Do you guys also see how when we attacked here, look at that. We have OH and OR coming off this whole thing after we deprotonate. Do you see how the R is inside of the molecule? Technically, you're not attacking with an OH, you're attacking with an alcohol. Why am I saying you're attacking with an alcohol? Well, let's go back to our OG molecule. If you're taking this aldehyde and you're attacking with this is not a hydroxide group. This has an R group attached to it. So this is the same as attacking this guy with ROH. It just so happens that they're attached. Does that make sense? So isn't that going to make a hemiacetal? Stay with me. Stay with me. When we did this, does the chirality matter? Yes, it does. Because here you're going to have plus minus. Why? P orbital. Right? Yes? So that means the OH and the OR can go either way. I forgot to mention that in the beginning. But this is very important to our discussion right now. What happens if you have something like this that stands up like that has a bunch of groups like this, and 6 carbons away at 1, 2, 3, 4, 5, 6 membered ring, you have an OH next to something that could get protonated inside the human body, somewhere. So when this thing gets protonated by some, I don't know, amino acid, this guy looks at that and says, yo, I can attack there. But what's attacking? Is it a hydroxide group? No, it's an alcohol. It's an alcohol group built into the same molecule as the aldehyde. So now, when you attack here, what do you get? Let's take a look. You get the 1 carbon connected to the oxygen that attacked. This is 6. We go 5, 4, 3, 2, back to 1. On 1, we have an aldehyde with a p orbital. Can we tell which way that's going to go? No. You can go front or back, which means that this can go up or it can go down. So we're going to put it on a little squiggle. 2 has an OH group on it. 3 has an OH group on it. 4 has an OH group on it. And 5 has a carbon and an OH group on it. That is glucose. Glucose, in its ring form, is a hemiacetal. And the difference between the 2 anomers of glucose, watch this, stay with me. The difference between the 2 anomers of glucose, anomer meaning one enantiomer of glucose, one diastereomer of glucose and the other that differ at this position right here, the hemiacetal carbon. If they are different at the hemiacetal carbon, they are known as anomers. Where did that anomeric shift come from? If you attack this p orbital on the back, you'll get the first anomer. If you attack it on the front, you'll get the second. There's a 50-50 shot of either one happening, so they both happen. Does that make sense? Do you guys follow how we built from alcohol to internal alcohol to glucose? That is why the anomeric carbon is the way that it is. The anomeric carbon exists in that way because of the fact that it was once an aldehyde being attacked by an internal alcohol on either face of the p orbital. These are called glucose anomers. They differ by a single OH group on the anomeric carbon position that was originally the aldehyde. In the straight chain form, the anomeric carbon is the aldehyde. And this helps so much when you're drawing between the 2 configurations. If you can just look at this and say, oh, that's that. And I can draw everything else. You guys got that? Does that make sense? We're going to see this again in biochem. This is very important to understand. Glucose is a hemiacetal, right? That's why we learn hemiacetals in orgo in the first place. But there's another term on there, the acetal. What does that look like? Very simple, very easy, but it's not super important on the MCAT, so you can take notes if you want to. You don't necessarily have to. What will happen here is that between the OR and the OH, something will continue to be protonated, because remember we left back a ROH2+. If we protonate this, one thing we can do is protonate the OH. Electrons from the OR can come down and help to kick off the H2O. That will give you back a protonated group like this that has the R attached to it. Now another molecule of the solvent, the ROH, can come and attack here. And you guys see where this is going. OR, OR. H. And deprotonation of that will cause bilateral existence of the OR groups. This is acetal formation, which just tacks onto the side over there. And we can actually, you know what, if you guys want to take photos or whatever it may be, if you guys want to screenshot this later when you're watching the video, we can actually just put it over here. Drop. Positive charge. Solvent in excess. Neutralize positive charge along with addition of the adduct. Solvent deprotonation leads to formation of the acetal. And for a ketal, replace the H with an R. Done. Do you understand? You're so hot, man.
Thanks, you too.
You guys understand? Tautomerisation. Very easy. Very, very easy. You guys want me to leave that? You guys okay with this? All right. He's like, no, I don't want to stare at that. I have one more week. One more week until I have to look at that for the rest of my life. Did I ever tell you guys why glucose is like the sugar? Did I give you guys that lesson? It's really cool, actually. It's very quick. Hey, do you guys remember chair formations? You guys don't really get asked about them on the MCAT that much, which is why I don't teach them, and also I think they suck. So, look at glucose. I'm gonna shoot myself is what I'm gonna do. I'm gonna draw glucose like this. I'm gonna draw it like that. Okay. You guys see this? Let's draw, you guys don't need to do this. Just look for a second. Let's draw glucose in the chair. Okay? That's the chair. OH, let's make OH go up. Then this guy goes down. Then this guy goes up. Then this guy goes down. Then this guy goes up. Do you notice how every single group is equatorial, not axial? So the overall addition of energy from the substituent groups is 0 kilojoules. It is the most stable sugar in the chair formation. That's why it's so predominant. Unless you do the other enantiomer, in which case you get one of them being axial, right? Make sense? Very good.
Is there a certain enantiomer that's more beneficial in all the
I'd assume beta. I would assume. I think there's like a slight preference for the one that's a perfect chair. I think it's like 0.1%, something like that. I don't know. I have to look into it. If you guys want to take a break, you can. I'm going to set up for the next lecture. I'm going to keep recording, but if you guys want to go stretch your legs a little bit, feel free. We're going to continue talking about enolates. So I'm going to literally like take a walk. Like I'm going to draw the same diagram we had just on the board like 2 seconds ago. Okay, so enolates is going to begin with the anatomy of the carbonyl again. Let's take a look at the anatomy of the carbonyl. Take a look at this. And we're going to really focus and hone in on one. Wow, you guys are so boring. I'm telling you to. Should we all just take a break? Should we all just like disappear? Should I stop the video? Can you guys leave? Like, oh my God, you guys hate yourselves. Okay, we're gonna start with the anatomy of the carbonyl again. The withdrawal,
What is this for? Sorry.
for chapter 7, enolates. Enolates and anions, right? The withdrawal of the electrons from this position is going to cause slight withdrawal this way. And we know that we have hydrogens at these positions. And what I want to focus in on is the ability to withdraw H+. The ability to withdraw H+ is not only bolstered by the fact that we have withdrawal of the electron density from those two bonds, but also the fact that the removal of the H+ is supported by the fact that the electrons left behind will be conjugated to a p orbital system. Now we have the p orbitals here and here that can support those electrons. What do I mean by that? Right? What I mean by that is, let's say that you have something like this. Let's do the aldehyde. I don't like drawing the hydrogen on the aldehyde. You guys are grown now after the past 20 minutes. So now we're going to draw it like this. Now in this chapter, it's not protonate the carbonyl, it's, oh wait, whoa. Everyone back up. Everyone back up. Back up. Tautomerization. Tautomerization is the ability for a ketone or an aldehyde to swap between two specific orientations of existence. It's basically the same molecule, showing itself in different ways. These are called tautomers. There's two mechanisms. There's an acid catalyzed mechanism and there's a base catalyzed mechanism. Let's do the acid first. Whenever we have acid, what do we do? What do we do when we have acid? Protonate the carbonyl. Yeah. That, along with the fact that, remember I said this is being withdrawn like this, and this is being withdrawn like that, so this hydrogen right here can be taken, right? Which means that the H2O, in a similar fashion that we saw before in some reactions, can come here, take this, drop these electrons that way, and kick these up, correct? And what that's going to do is it's going to create something like double bond OH. It's a mix between something like a dehydration and a carbonyl reaction. This has a specific name. The double bond is known as an ene, and the OH is known as an ol. This is known as an enol. A double bond with an alcohol on it. The proper name for this is a, hold on. Is it, no, vinyl is next to a double bond. I forgot what this is called. Oh, I forget. I forget what the proper organic term for this is. Vinyl means you can resonate into that position, I believe. I forget. There's a name for that. This is known as an enol. It's where the alcohol group sits on top of a double bonded position. So this is known as the ketone, and this is known as the enol. This tautomerism is called a keto-enol tautomerization. You will see it a lot. A keto-enol tautomerization. Believe it or not, this happens as part of glycolysis. This happens in a specific step of glycolysis. Do you guys know phosphoenol pyruvate? It is an enol. It is an enol that's phosphorylated. What is more stable, the ketone or the enol? The ketone. So actually, it looks like this. Looks like that. Short arrow forward, long arrow back. Keto-enol tautomerization. Let's do base. H2O OH. I'm going to take that labile hydrogen. I'm going to drop off the electrons here. I'm going to make a carbanion. I am going to resonate these electrons. Remember I said the electrons, actually this is a pretty good place to go from where I just said. The electrons are supported by a p orbital system, right? That is going to resonate in like this and kick up these electrons this way. Yes? Remember we made H2O on the side from picking up that hydrogen using the hydroxide, right? You guys get that? Resonance gives us and now if we take the water and we deprotonate with that, giving us back our base, which means catalysis, we get the, this is such a crappy diagram. We get the enol. Base and acid catalyzed. And here you reform the acid. And here you reform the base. And understand that everything can go backwards in the exact opposite orientation of what you just saw. How you doing, man? I'm so tired. I knew this lecture was going to take like everything out of me. I'm exhausted. Still got one chapter to go. Oh my God, good luck watching this. Enolates. Now that you know what an enol is, it shouldn't be hard to know what an enolate is. If I add ate to the ending of something, it means what? It means? I have sulfur, I have sulfate. No, well, yes, it does technically, but what else? It's negative. It's a negative ion, right? So an enol, if an enol is this, what do you think an enolate is? An enolate is that. Yeah? That's an enolate. We saw that before. Go back in your notes. Where'd you see this? It was right here, right? An enolate. So the way we, and someone remind me, how did we get to the enolate? Which mechanism, the acid or the base? So the enolates come from base reactions with aldehydes and ketones, okay? When you do base chemistry on an aldehyde or a ketone, you're going to get an enolate. So let's take those enolates and do some chemistry with them. This is something known as the Aldol reaction. Even before that, hold on. Even before that. Let's take a look at this. Feels so bad. Every time you give me your markers, I bleed them dry. Drop that hydrogen. I said base catalyzed, right? Base reactions. Boom, 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 right? That's going to give us an enolate. What did the intermediate of that look like? Remember that when we did this, what actually we did was we dropped these electrons onto the carbon, right? We made a carbanion that is conjugated in the system with the p orbitals. That negative carbanion is going to resonate into the p orbitals like this, and these are actually two resonance contributors. And this one's more stable because the oxygen's better at carrying the negative charge. Remember I told you about that in the beginning of the lecture? Very good. This is chapter 7. What's up? I'm surprised. Everything's like working today. That's so nice. Oh, let's go. I need like an expo marker sponsorship. Like they need to send me like a box of their markers or something. I swear by these. They're really, really good. I've never used better markers. I've used a bunch of different markers. There's nothing like an Expo marker.
You want a Costco pack?
That'd be great. We just go through them. We'll probably use all of them in biochem. All right. So what chemistry can we do with these? Well, one thing we can do. What happened? Wait. That's right over there. It's in the previous slide. Look at that. Now what do we do? Oh my goodness. Where am I going to take from? HA or HB? Why? More substituted. And that makes sense until you realize that that's a negative with 2 donating groups on it. But is it? No, that's a withdrawing group over there. And it's resonant, which means that when it's resonant, you're actually going to resonate these in, and you're going to end up making the double bond, which is more substituted. You guys are absolutely correct. This is the right way to do it. Double check my notes, make sure I'm not giving you guys any wrong information. Good. So those positions, those alpha carbon positions, are slightly, right? Slightly acidic. A little bit acidic. They can be abstracted, right? They're a tiny bit acidic. They can be removed. The removal of the proton, that's a Bronsted-Lowry acid-base reaction. Remember I told you, all of organic chemistry is just a bunch of acid-base reactions. That removal is a Bronsted-Lowry acid-base reaction. All right. Now let's do chemistry with these. We are going to do the Aldol reaction. It is called the Aldol because you use aldehydes to make alcohols. And this is a way of making carbon-to-carbon connections using aldehydes. You begin, I am going to draw them a specific way. I want you to draw them that way. Normally you draw your aldehydes facing left. We're going to draw them facing right. We have, I know it's going to look super weird, we have an aldehyde. I know you don't like it. I don't like it either. It feels weird because your arm is going the wrong way, right? We have an aldehyde. We put just a little bit of base. Remember, we hang the hydrogen. When we do bases, we hang the hydrogen. First thing we do is form the enolate. That's why it's in this chapter. I'm just going to show the shortened version. That's going to give us an enolate. See, I already did it backwards. Now what? If we attack the water, we just go backwards. We produced a water molecule here. If we take the proton back from the water, we go backwards. So what else can we do? What else is in the flask? What else is in this flask? More aldehydes. Do you guys remember when we talked about the chemistry, the anatomy? Sorry, we talked about the anatomy of the carbonyl. Do you guys remember what position was an electrophile? The carbon of the carbonyl, right? The carbon of the carbonyl was an electrophile. This guy is very electron rich. This removal was a Bronsted-Lowry acid-base reaction. If an electron-rich species targets an electron-deficient position, that is a Lewis acid-base reaction. What's going to happen is the enolate can push its electrons, and what happens is we literally fold open this bond. The bond folds open to that electrophilic position. I'm going to show you very intentionally that this is partially negative and this is partially positive. So that partially positive position is the one that's getting attacked, correct? So now, when we pop that open, the carbon can't accommodate that many bonds, so we transfer the electrons up. This is the Aldol move. This is the Aldol right here. Yeah? You guys see that? You guys get it? So now what are we going to get? Professor Militsky always said, draw what didn't change and then draw what changed. So what didn't change? We still have this oxygen, still have this bond, we still have a single bond, and we still have this single bond and this single bond. Now we draw what changed. What changed is that these electrons on the oxygen came down to form a double bond. This bond popped open to connect here, and this bond popped up to become electrons over here. That is your intermediate. Yes? The bond we've created is from here to here, which connects this to this. Yeah? What bond is that in reference to our aldehyde? In reference to this, our aldehyde, what bond is this? This is known as the alpha-beta bond. The alpha-beta bond. That's the one that we made. Beta. The alpha-beta bond, right? Now, we have water floating around the flask, right? Proton transfer from the water gives us what? Gives us a alcohol, like I told you in the beginning. That's the product. We made an alpha-beta bond, and on the beta sits what? A hydroxide group. This is known as a beta hydroxy aldehyde. Or more generally, a beta hydroxy carbonyl. That is the product of the Aldol reaction. Can you do aldols with ketones? Yes, you can.
Why don't the electrons just move down and then form like an aldehyde and a ketone?
Why don't the electrons here move down and form a ketone? Yeah? Can't accommodate 5 bonds on carbon. Not allowed. Remember, there are implicit hydrogens where I don't draw them. And I wish that was the end of the story. Because if it was, that would make your life a lot easier. Because not only do you need to see this and identify, oh, look, a hydroxide group 2 positions away from an aldehyde, that's an aldol. So what you can do, how do you reverse this? Beta hydroxy, find the alpha carbon, the beta carbon. Find the alpha and the beta. Erase their bond and turn the alcohol back into a aldehyde. That's how you reverse it. That's a trick for the MCAT. You cut it, turn it back into an aldehyde. Now your life is about to get really, really crap. Because not only do you have the beta hydroxyaldehyde, some chemists, they say, oh, well, this is a basic reaction. Why don't I finish the reaction with an acid wash? I'll wash the whole flask with acid. So they add acid to this flask. What happens when you add acid to a secondary alcohol, like I said in chapter 5? What reaction do you get? An E1 reaction. But this is one of the examples where we use the E2 reaction. Remember I said secondaries can go either way? This is what I was alluding to. So now when we protonate, we actually get this. And now we have this hydrogen right here that's very available for removal because it withdraws and withdraws in 2 directions. And now the water in the flask, we'll take that and move, and now we get this. So not only do you need to identify the beta hydroxyaldehyde as a product, but you have to know that when acid washed, you know that alcohols and acid dehydrate. And they dehydrate in the position of the aldehyde. This is known as the alpha-beta unsaturated aldehyde. Alpha-beta unsaturated. Unsaturated meaning it's not saturated with hydrogens as a double bond there. So you need to identify that and see that it's an aldol as well. How do you reverse this? So look, I said you reverse this. How do you reverse this? You reverse this by taking the alpha-beta bond, erasing, and turning the alcohol back into the aldehyde. How do you reverse this? Alpha beta bond, erase, and take the terminal of it and turn it into an aldehyde. Take the beta terminal, alpha beta bond. That's the bond you made, right? Delete the bond you made and turn the beta terminal into an aldehyde. That's where they came from. Why do I keep harping on where did they come from? Where did they go? Where did they come from, Cotton Eye Joe, right? Why am I harping on that? Because on the MCAT, you're going to see stuff like this. And they're going to ask you, what were the substrates used to make that? We're just going to finish the recording real quick. My phone died, so we just have a couple more things to go through. The first thing is identifying how aldols are formed and how to reverse them, right? So if you have, oh my God, let's get rid of that traumatizing stuff on the board. If you have an aldol and you want to be able to reverse the aldol, what exactly do you do? Well, we know there are two things that form from the aldol. You can have a beta hydroxycarbonyl or you can have an alpha beta unsaturated carbonyl, right? So let's say that you have some random molecule. And from this molecule you say, oh, well, that is a beta hydroxycarbonyl. I will find the alpha beta bond and I will erase the alpha beta bond. I will destroy it. And then with the alcohol, I will turn it back into the aldol. Those are the starting materials. I drew this starting material because I wanted to ask you, does it matter which one of these was the enolate? Yes, it does. Because here, you will see that you actually don't have any alpha hydrogens. There are none. So this guy had to be the enolate. In certain cases of the aldol reaction, it doesn't matter which one's the enolate. Both of them can be. In this one, it definitely matters. Because that benzene ring, this carbon right here is the only alpha carbon because we're an aldehyde, right? Already has 4 bonds. You can't have any hydrogens on there, right? That's how we reverse the aldol. Same thing with the alpha beta unsaturated. You just erase it, right? So if we have something like a alpha beta unsaturated, alpha beta unsaturated, alpha beta, we erase this, beta terminal becomes a aldehyde. Does this one matter? Well, still yes, because if this were going that way, it would look different. This is going that way. This is attacking that, because that was the hydroxide. Some aldols, it doesn't matter, because usually when they're symmetrical, it doesn't matter. We have to talk about 2 more things. First is the Claisen condensation. The Claisen condensation is an aldol done with this molecule. It's an aldol done with this molecule. And now the first thing we want to try to do is use the OH in order to get the enolate going. So what we do, when we have the OH, one thing that can happen, actually, is that we can attack like this. I'm just showing you this because I'm going to show you why it doesn't work. We actually can't use the OH in this example. When these electrons come back down, we can actually kick off this group. And what that does is it gives us a carboxylic acid that will be rapidly deprotonated by the ethoxide anion, and we're going to get the carboxylate and ethanol. That kills the reaction, because now you can't do anything. Ethanol and carboxylate don't react. So what we actually have to do is we have to attack this with something that can't kick off that group. The only thing that can't kick off that group is that group itself. If you attack with the group itself. So what we do actually is we attack with sodium ethoxide. Because now if you attack with this and you kick that off, you kick off the same thing that you attacked with. It's redundant. So now finally we're ready to do the actual aldol. So like before, we take this hydrogen, we make the enolate. We make the enolate with this hanging ester group. right? Then we take another molecule of the ester, and I'm going to draw this out explicitly. OET has this. This connects to a carbon. The carbon has OET. Oh, sorry. This connects to a carbon. The carbon has OET, O minus, and a CH3 group. Electrons come down to kick off the OET. We get our final product of and the important thing that they want you to know about the Claisen is that these hydrogens right here are actually very acidic. Because of the fact that if you deprotonate them and put the carbanion there, it can resonate into two positions. There's one last thing in this chapter that we need to touch upon. You guys don't need to take notes. It's very low yield. But I want you to be able to see it just in case you see it anywhere in the world, not just on exam day. Let's say that you have an aldol. And you do the aldol to completion, meaning step 1, OH minus, and then step 2, acid wash. You're going to get a alpha beta unsaturated, correct? This alpha beta unsaturated is going to then get put in a flask with more aldehydes and OH minus. The aldehydes and OH minus are going to make enolates. And what happened, this is super weird reaction. The enolate can attack the double bond, flip up this bond, and kick this up. This is complicated chemistry. Doesn't really come up all that often. Just want you to be able to identify it. So that's going to look like O down double bond up to this and like that. And that's going to create an O minus right here. In this flask, we have H2O from the deprotonation and all that stuff, from this aldol enolate formation. H2O will give up its proton. And just like earlier in the chapter when we had OH with a double bond here, this enol will become a ketone through a keto-enol tautomerism. In what way is that going to happen here? I guess I can show you the reaction. If it's base catalyzed, it's going to be like this. Then we have the H2O that came from the deprotonation. And this can come down, come like this, and go like that. And that's going to give us the hallmark of the Michael product is that we have 1, 2, 3 carbons between carbonyl groups. That is the Michael addition. Very lowly tested, not super important.
If you do an Aldol reaction, you gave us like symmetrical groups and one where you had no alpha hydrogens. What if it's two different structures, but they both equally have alpha hydrogens? Is it just two different?
It depends which position you take them from. So do you want to see an example?
Yeah, like how is it two different products?
Yeah, it's literally different products.
Okay, so
Yeah.
it doesn't matter which one.
So let's say that you have something like this. Right? And you have something like this. If you take the hydrogen, I'm going to say HA, HB, HC, HD. If you take HA, your enolate is going to look like this. Right? Which means that when you attack, oh my God, why am I doing this to myself? When you attack, you're going to get something like that. So you're going to get 1, 2, 3, 4, double bond O, like that, and then this carbon is going to connect to a oxygen that has a methyl group and that. And then this is going to become an H. Alpha, beta hydroxy. Let's do, that was HA, let's do HC. Let me clean this up. That, HA. If I mess this up, don't blame me. It's complicated. HC gets taken. You can use something like LDA to take from the less substituted side instead of the more substituted side, right?
You would need LD.
Yeah, because it's a bulky base. It's going to prefer the less substituted side because of steric hindrance. You're going to go boom, boom, bam, right? And you go 1, 2, 3, 4, O minus. The group on the O minus connect into this guy, connect to this carbon, which is connected to the double bond O. And that's if you take HC. Completely different products.
So you'd have 4 different products.
Yeah. If they're asymmetrical on all sides, you have 4 different products, depending on where you take from. So to take from HA here, if you put LDA in this one, you'll take from HA. If you put OH minus in this one, you'll take from HB. If you put OH minus in this one, you'll take from HD. And if you put LDA in this one, you'll take from HC. And then what you do is you put the LDA in here, reflux it, and then add your other aldehyde, and then, or the ketone, and they're both ketones in this example. You add the other ketone, you'll get the product that you want. Thank you guys so much for watching. Please support the channel down below. 50% of all donations go to Doctors Without Borders, and then we'll do the donation at the end of this month. I'll send you guys a receipt. See you next time. Enjoy studying.